waste. Today featuring the topic of biochar. So we had a lot of engagement this year on topics such as black soldier fly, organic waste treatment and biogas, but also other topics. And now we will have, I think, the second ever meeting of the group focusing on biochar. The last one was about 2 years ago with a case study from Nigeria. Let me just start by some housekeeping rules. So this session is recorded. So if you unmute your microphone or you turn on your camera, you will get a notice that you have to agree to the privacy conditions and agree to being recorded. If you turn off your camera and mute yourself, then of course you will not be recorded. We will share the recording afterwards in the Prevent Waste Hub. We will have a couple of presentations today and other inputs. So if you have any questions about these, please feel free at any time to use the chat to ask your questions, and then we will take them when the presentations are done. And we will have focus on any chatbots, any note takers or otters or other types of chatbots who enter the chat, and we will delete them from the chat. If you have an option, just make sure that you're not accompanied by an artificial intelligence chatbot. Okay, so we will today have many inputs. Usually we have 2 or 3. Today we have a bit more, so I will be very strict on the time management today, and have presentations from around the globe, a couple from Europe and Latin America, but we will also have some impressions from the African continent today. And yeah, I will say more about each topic when we come to the presentations. We will probably allow for maybe 1 question after each presentation. If you have a direct question, a technical question, and we hope to have a discussion at the end. It might be a bit less than 30 minutes, but we will try to make it as long as possible. With this, I give the floor to Karina for news and a general presentation of the Prevent Waste Alliance. Please, Karina, go ahead.
Thank you, Martin. Good day, everyone. Nice to meet you. Some of you already know me and some don't. Since we have opened this meeting to also externals who are not yet Prevent members, I'm just going to give a short recap of what Prevent is. And if you enjoy this meeting and you think Prevent could provide some benefits for you and you could fit in, then I also warmly invite you to become a member, which is quite easy. I will also post a link in the chat afterwards. So the Prevent Waste Alliance is a think and do tank. We have currently more than 600 members from around the globe, and we work in different groups such as plastics, e-waste and batteries, or organic waste, where we are at now. And then we also have some other cross-cutting topics like financing, digitalization, or awareness raising, and also other subgroups like EPR, reuse, and so on. So I think everyone who works in circular economy will find one or the other group that is really relevant to their work. So we have also some great options how to participate in Prevent as a member. You can hold your matchmaking session and therewith present your organization to all Prevent members. You can interact with other members, of course. You can start projects, publish studies, and so on. So there's really everything is possible. Of course, we also have some support that we only provide to our Prevent members. For example, our finance help desk, where we try to help you how to approach funders and also find the right funders for your organization. So yeah, if you're not a member yet, maybe have a look. Next slide, please. And these are the latest news from our network, mostly relevant to our current members, of course. So we have the organic waste working group meeting, the last one of the year, this Wednesday. So if you don't have an invitation yet, please contact me or Martin, then we will send you the link. maybe I can also put it in the chat. It's really important that you come if you have time, because we're deciding upon the topics that we'll focus on next year, for example. Then, of course, a General Assembly, 10th of December. Every Prevent member should have gotten the invitation. If not, please contact me. Most important meeting of the year. There we will also hold the steering committee elections, and we'll publish the annual member survey. So these are the most important points, I think. Next slide. Yep, and that's it for me. Thank you.
Thanks for keeping it short, Karina. As I said, we have many inputs, and we will just start right away with our first basic introduction input shared by Herwig Ragossnig and Amzy Vallenas. Herwig is the founder of Carbon Turnaround, which is a consulting and project development company with the aim of to decarbonize our economy by using circular economy principles, and he focuses a lot on organic waste valorization. He's using black soldier fly approaches, but also biochar for methane mitigation. And he's one of our most active group members in the organic waste community. And he's actually also the person who had the idea, who proposed having this meeting today. And Amzy Vallenas is a circular economy specialist. She works at Reciclame, Peru. And also glad to have her here as a partner of Herwig in this presentation. So I give the floor to you, Herwig, and you, Amzy, now for your presentation.
Thank you, Martin. I'm trying to... Cannot proceed, but I took over control, Martin, but it's not moving.
Okay, strange.
Can you hear me? Yeah, I took over. I will stop again and do it again.
Okay. But
can you share again? That was sorry.
Yes. Sure.
This was the wrong.
It's loading. I think it's a big presentation. That's why it takes a bit.
I take over control.
Okay. Yeah. Okay. Now it should work.
But it's not proceeding.
Then I can also take control. No change. Okay. Yes. Okay.
It was okay.
Okay. Go ahead.
Okay. Thanks a lot. I will be also quite short because we don't have much time. So thanks a lot for the introduction. The presentation which I'm going to give together with Amzy is giving a rough overview about biochar, why this is interesting, why we are trying to promote this, and what could be the role for organic waste management globally, especially in the global south. So Martin already presented Carbon Turnaround. So we are working globally on different circular economy solutions in order to decarbonize economies and companies. Regarding biochar, for those which are not familiar with biochar, what is it? It's a type of charcoal-like substance, but it's not charcoal, and this is very important to differentiate. And it is produced out of organic waste through a process which is called pyrolysis, and you can transform organic material in a kind of inert biochar, which can be used for different applications. The good thing is the pyrolysis technology is suitable for many different organic waste streams. And in general, you can say you can produce out through the pyrolysis, you can produce out of biomass three main products, which is biochar, syngas, and pyrolysis oil. And on the next slide, you can see different types of processes of pyrolysis solutions or technologies, because there's not just one type of pyrolysis. There are different pyrolysis technologies available for different, for example, different material or different products which you want to generate. When we talk about biochar, normally we talk about slow pyrolysis because there the biochar output is higher than, for example, in the case of fast pyrolysis, where you are more focusing on the liquid pyrolysis oil. So we have here different pyrolysis solutions available for different aims. Biochar is one of many different solutions for organic waste valorization. So this slide, it's very small, but maybe you can see it's summarizing a little bit the most common organic waste valorization solutions. And pyrolysis is a type of thermochemical treatment of organic waste. And we see biochar or pyrolysis in general as one pillar for organic waste management, because different organic waste streams have different characteristics, and there are different solutions suitable in order
today
to
featuring the
treat
topic
them
of
or to
biochar. So we had
valorize them.
a lot of
And biochar should be one of these solutions for certain type of organic waste streams. There are a lot of benefits if we talk about biochar. And one of the most important ones is definitely climate mitigation. We can valorize organic waste and avoid landfilling, and therefore methane emission can be considerably reduced. And as Martin said, we are also working in BSF solutions, and this is, for example, BSF is very suitable for food waste organic waste streams, and pyrolysis is, for example, more suitable for lignocellulosic organic waste streams. So we have here an interesting solution to divert organic waste from landfills. But we have also other benefits, like, for example, the production of renewable energy out of pyrolysis systems. We have recycling of nutrients. We can improve soils by adding biochar, improve their nutrition balance, and store carbon in soils, what is improving soil health. And as already said, we can reduce landfilling and therefore have here another additional benefit. Important to mention, why is biochar such an interesting tool for climate mitigation? It's the length of time which biochar can stay in soils, because through the pyrolysis process, the carbon is transformed in a kind of stable, inert carbon, and it can last many hundreds of years or even thousands of years in soils, and therefore the natural decomposition process is somehow interrupted, because for example, organic material, when it's decomposed, the CO2 is not emitted immediately. It can be transferred in an inert substance in biochar and stay, if you apply it to soils for a very long time, with all the benefits I mentioned before. And therefore, we can proactively extract carbon from the atmosphere. The most common use of a biochar is for agricultural usage. This is the traditional way how it is used. Amzy will show a little bit later that there are also other use cases for biochar, but in agricultural use cases, we have really a very powerful tool to have many benefits for agricultural production. One, of course, is this permanent storage of carbon in the soil. This has a very positive effects on the health of soils and the vitality of soils. it has shown that biochar can improve significantly the productivity of soils, and the plant growth can benefit very much if biochar is used. It also has a very positive effect on the water efficiency of soils, because biochar is acting as a kind of spongy and can store water during longer term, and therefore in areas where, for example, due to climate change, rainfalls are decreasing, it can help to adapt to climate change. And it also can store, or it's storing like a spongy nutritions, and therefore it acts as a kind of slow release fertilizer, because depletion of nutrients in soils is avoided, and this has a very positive effect on plant growth. I will not talk much about pyrolysis technology, because in the other presentation there's more covered about this, but important is to differentiate a little bit about two types of systems: the batch systems, where you have, for example, in an earth kiln, you cover your biomass, and you have condition without combustion, without oxygen, and the material is transferred to biochar. This is, let's say, the more traditional way how this was done in the past, but continuous pyrolysis systems, they work like a modern bioenergy plant in a continuous way, and you can produce much higher quantities and a more consistent product quality, and you can control much better your emissions. This is for new biochar plants normally the way how it is used. This slide I don't want to say much. It's just showing a typical setup of a modern continuous pyrolysis plant. As already said, it's very similar to a bioenergy plant. Very important is the certification of biochar. If you want to scale up and have a guaranteed product quality, and this is important for different reasons, of course, for attracting investors, and also for the generation of carbon credits, which is a very important part of any large-scale biochar project, as I will show you in a couple of slides. Biochar is really it's a multi-talent if we talk about sustainable development. So we have here positive effects on climate mitigation, climate adaptation, generation of green jobs, improving food safety in regions where soils are poor, because you can improve the soil quality. Also the water aspect I already mentioned. So we have here really a lot of positive effects on sustainable development. One of the most important drivers for biochar is the direct carbon removal. We see here in the last years a lot of development to promote solutions which can extract proactively carbon from the atmosphere. And from all the options which we have available, biochar is most likely the most advanced and the only one which is ready technically to scale up. So we have here an interesting market which is in development, and there are prognosis which shows that this direct carbon removal in the years to come will significantly grow. This has also to do with the not reaching of climate goals, and therefore alternative solutions to reduce the carbon concentration gaining a lot of interest. And this slide shows a little bit the development of biochar plants in Europe. As you see, by 2024, have been already 200 biochar plants in operation in Europe. And we see now, also, especially in the global south, also a lot of new development with biochar.
Herwig, I think you only have 2 minutes left for both of you. So
okay, so I will skip this and just one word. In the global south, there's a lot of potential, and we see here, as said, a lot of developments in that regard. Amzy, sorry for that. I give it over to you. So.
Yeah, no worries. I think we'll see a lot of the global south potential in the other presentation, so it's okay. Can you pass it to the next one, please?
Yes, I will.
Should I pass it myself? Okay, yeah. So not all biochars are created equal. Depending on the pyrolysis conditions and the biomass that is used, the biochar or biochars will come out with different physiochemical properties. And then these physiochemical properties will heavily influence what can your biochar be used for. So for example, low temperature biochar, so below 500 degrees Celsius, will have more unpyrolysed organic matter in the particles, so more residues from the original biomass, and that equals to more volatile functional groups in the surface and a higher hydrogen to carbon ratio, which is a very important indicator when you're trying to get produce carbon credit removals from it. In the contrary, like high temperature biochar will have a more graphite-like structure, so not a lot of functional groups on the surface, a lower hydrogen to carbon ratio, and probably a higher, because of that, a higher carbon content. So all of this is influenced by the pyrolysis conditions, as I said, and they will influence the application of your biochar, what can be used for, and also if you are trying to achieve a certification of it from it or carbon credits from it, it will be something really important to look into. Some properties can be altered.
Amzy, are you still there?
Yes. Hello? Can you hear me?
I can hear you well. I can hear you well, Amzy.
Amzy, can you hear me?
Yes.
But I can hear her, Herwig.
Martin, can you hear me?
Yes, I think it's
Yes.
on your side. Just go ahead, Amzy.
Yeah, so just to mention that some properties can be altered through
Martin,
chemical or physical activation by using things like acids or hydroxides to modify the surface of the biochar, or things like steam activations to increase the specific surface areas or the porousness of the biochar. So as I said, all of these properties will influence what the biochar can be used for. And not all applications generate carbon removal credits. Part of the obtaining carbon removal credits is to assure the permanence of the biochar. And that's a really important aspect. I lost sight of the presentation.
Yeah, same for. I think it was Herwig. I think he had the control.
Oh,
I'm resharing it.
Okay. Yeah, no worries. It's just a couple more ideas. So as I said, as Herwig said, the most important application for biochar right now is in the agricultural industry. However, depending on the characteristics of the biochar, then we could, sorry, I'm just going to jump into the slide that we were, I think it was this one. Yes. Okay, perfect. Thank you. Sorry.
Is this the right slide? Broad spectrum of biochar applications?
Yeah, this one. Okay.
Okay.
Sorry. As I was saying, some applications require very specific characteristics, and some applications are a little bit more flexible. So just as a few examples, we've talked a lot about agricultural, but for example, biochar can also be used in water treatment in replacement of activated charcoal. For this specific use, a better biochar is a biochar that has a high specific surface area. So we're looking at 350 square meters per gram or more. And depending on the pollutant that is trying to be removed, maybe activation or modification will be required. So something like iron impregnation or acid or alkali modification of the biochar. And it's for this application specifically, it's very important that the biochar doesn't add any more pollutants into the water. In comparison, for example, if we want to use biochar for concrete, it doesn't really matter if the biochar has a higher ash content depending on the mineral composition, but it does require a specific particle size because it's going to affect the mechanical properties of the concrete. And if we're looking at, for example, biochar in the metal alloy industry, which is gaining a lot of talk in Europe specifically, what you're looking at is that fixed carbon fraction of the biochar. You want that to be over 70% and sometimes even over 85%, and requires very low sulfur and nitrogen content. So as you can see, these are just some examples, and depending on the application of the biochar, you may be eligible to produce carbon credits from it, or not, but also you may have a lower or higher value of the biochar itself because it's tied to the business and the production on what is it going to be used in. So I think that's the end of our presentation. And just to not extend the time anymore, I'm just going to pass it back to Martin. Thanks.
Thank you so much, Amzy. Thanks. I forgot to mention that you're not only doing the international cooperation project at Reciclame, but you're also a PhD candidate at the University of British Columbia, also focusing on industrial waste, recycling, and biochar innovation. So sorry for not saying it in the beginning, but yeah, we are doing it right now. And I said we would allow 1 or 2 questions per presentation. We are already very much behind the time. So I think 1 question would be good. I'm afraid we lost Herwig. No, he's back. He's back. So I will just read 1 question from the chat, and we can leave the other questions for the discussion. So a question by Hetze Rodenburg-Felmart. His question is, are there any convincing data on how much water can be saved on the farm by adding biochar to the soil? So Amzy or Herwig, could you please share your perspective on this question?
I can answer that. I think it's going to be very highly variable. And unfortunately, what I've seen is that it's very case by case kind of thing. Biochar does increase the water holding capacity of soils, but specifically a number of cubic meters per hectare that you can save from a specific culture, it will need like further research and probably even a specific testing.
Great, thank you. Dirk, you're raising your hand. If you can say something in less than 1 minute, then please go ahead. If not, we would save it for later.
Yeah, just a question to the both credentials, and thanks for the presentation. We are also working quite intensively on biochar from GIZ side and have a working group. However, what we never can really encounter is real success stories. So I would be interested in if you can give us some success stories, also please in the chat if it's too short in time. And as well as what we also facing often the problem is that if it comes to carbon credits, you need project developers, but mostly one project developer is overloaded with too many tasks, linkage with carbon markets, source security, as well as maintaining the technology, because operating in an economic feasible way is very sophisticated. Maybe you have some suggestion from your side on that. Thank you.
You want to react quickly, Amzy or Herwig, please.
Yeah.
Go ahead.
Martin, I will try. Sorry, I had to connect with my cell phone. My computer does not like anymore to participate. Regarding success story, of course, it depends a lot, but there are in Europe companies which are specialized, for example, in niche markets where they sell their biochar. For example, the company Sonnenerde here in Austria is very successful. But in the global south, definitely there are many projects now doing very well. And we have actually 3 presentations about success stories in the global south today as part of this webinar. So this is something which is definitely the case. And regarding carbon credits, yeah, you need a certain scale in order to make this interesting for biochar projects. And there's a high demand for that type of carbon credits. The largest biochar project currently is in Paraguay. And this is a different business case. So you really have to see case by case what is the driver for such type of projects. But I think there are many positive examples regarding this type of solutions.
Great, thank you, Herwig. As you said, we will have some case studies later in the meeting. Manuel already took over the presentation, so we're also glad to have another insight from Manuel. He is the area manager for thermochemical technologies at BEST, and BEST is an acronym standing for Bioenergy and Sustainable Technologies. And Manuel has more than 2 decades of experience in combustion, pyrolysis, and gasification. So Manuel, you have 10 minutes. Please go ahead. The floor is yours.
Thank you very much, Martin, for this nice introduction. I think there was a small mistake still in the header of my presentation. I will not go and talk about biogas production. Instead, I will have a similar look on the view on biochar production as Herwig did, but a little bit with a different perspective. So I will be talking about pyrolysis and circular economy approaches. My name is Manuel Schwabel. As Martin introduced me, I'm area manager here at BEST, Bioenergy and Sustainable Technologies. We are a research institute cooperating with industry partners around the world, also with Pyrogenesis, for example, who will showcase one of their technologies later on in this webinar. But now coming a little bit more towards what is pyrolysis in detail. Most of you, I think, know it. It is a thermochemical conversion of biogenic feedstocks without oxygen. Now, if you heat up a biogenic feedstock, first, there will be an evaporation of water contents up to 150 degrees centigrade. But starting from then on, the molecules in the feedstock will start to vibrate and decompose into all different kinds of elements and of molecules, containing on the one hand carbon monoxide, hydrogen gas, but also all different kinds of organic matter. And these different organic matters can produce then gaseous components, as well as pyrolysis oils, liquids like Herwig showed you already, and also of highest interest in our webinar is, of course, the biochar, the solid residues from pyrolysis. Now, when we talk about a mass balance, and we talk all about slow to intermediate pyrolysis, which means that we have a residence time of the feedstock in this temperature about a couple of minutes to up to hours, then you can expect about 30% of the mass of the feedstock is transferred to biochar, to the fixed carbon. Now, when it comes to the carbon itself, on the one hand, about 50% of the carbon is stored actually in the biochar. So it is an enrichment of carbon in the solid residues, whereas the remaining 50% of the carbon is released within the pyrolysis gases or the condensables inside. On the other hand, if we talk about energy balances, it looks very similar actually then to the carbon balance. About 50% of the heating value of a feedstock is included in the biochar itself, which means if you transfer, for example, a wood chip or pellets into biochar, then you would store about 50% of your energy in your char, which is not available to bioenergy production. But on the other hand, it means also that 50% of the energy is still released with the pyrolysis gases and with the condensables inside, meaning that has a distinct value actually, which needs a valorization also. In our premise, we investigate all different kinds of feedstocks and test within our very unique infrastructure, laboratory and pilot infrastructure, all different kinds of feedstocks. In terms of a circular economy, we need to investigate and utilize all feedstock we have available. For example, if we have residues from river dam, storage here, which contains a lot of plastics inside, or walnut shells, which are currently combusted and provide the energy to the processing. Then we have investigated residues from compost screening overflow, which also consists of quite a lot of composting bags inside. And the good thing in pyrolysis is all of those plastic contaminants decompose completely to carbon dioxide, to carbon monoxide, or to volatile gases actually. And the remainings are free of plastic, also microplastics actually. We investigated on the other side also from food industry, different residues. You see here wheat bran, for example, from starch production. Of course, wheat bran has an own value itself because it is currently used in Austria for cattle feeding. On the other hand, you always look for better possibilities for upcycling of the carbon utilization. Therefore, we investigated also the biochar production for that reason. However, wheat bran has a very, very low ash melting temperature. It is about 500 to 600 degrees centigrade. And even if your pyrolysis temperature is below that melting temperature, you have actually severe issues piling up and melting of these biochar particles together, and therefore we had quite some issues out of our rotary kiln that can be extracted actually. Another example is also residues from coffee roasting. We had the epidermis of the coffee chaffs, which were already very they were already very light and needed to be composted because there was no other possibilities. So we utilized also tested it for biochar production. Now, when it comes from to application, Amzy told us already about very different possibilities how to apply it. I do not want to go in detail about all of them, but what we test in our premise at best is, of course, soil amendment, introduction of nutrients into the soils, and coverage of nutrients in the soils, as well as water holding capacities. Maybe one interesting fact on that one, the biochar itself can absorb up to 2 times of its water, of its mass in terms of water. That does not mean how much of water you can really reduce when you do the irrigation in your field, because it strongly, as Amzy already said, it strongly depends on how much biochar you apply also to your soil. But the biochar itself can absorb a lot of water because of its internal functional and inner surface. Also, we test at best, for example, introducing it into concrete materials, just using the carbon dioxide offset. You can introduced quite a lot already of biochar, but currently we investigate also how the functional groups of the biochar need to be prepared in order to have an added value also in the concrete and reduce even the cement mixture in the concrete by adding biochar. Also, application in metallurgy was already said by Amzy. Here, I think it is even more complicated. However, we are currently doing a project with the Austrian steel industry partner, and they have all different kinds of carbon qualities which they need to apply, strongly dependent also on the process of the metallurgy. For example, in the blast furnaces, currently we investigate the possibility for the PCI. This is the injector coal, which needs to be of very low particle size, of high carbon content and of low volatiles content. But on the other hand, they also need carbons at the different stage of the process with a high volatile content and a low inner surface. So you always need to design and engineer the biochar actually for the process itself so that they can directly implement it into their processes. Also, we investigate introduction of biochars into composite materials. Maybe a nice fact on the side here. We introduced about 20% of biochar into plastic composite material, making it electric conduct afterwards, which you can use after all for shieldings, for 3D printing filaments in order to functionalize your composite and your plastic materials. Also being said, I wanted to bring you another view on carbon dioxide removal. All over, with 1 ton of biochar, you can store about 2 to 3 tons of CO2. This strongly depends on logistics of the biochar, logistics of the feedstocks, etc. But where does that come from actually? You all know maybe this distinct diagram with increasing CO2 in the atmosphere. But if you scale into that, you always see that seasonal variations and fluctuations of the CO2 ppm. This is because of the decomposition of organic residues of the leaves of all the seasonal effects. Now, here comes biochar into play and the potential of pyrolysis in order to take about 50% of that CO2 and store it within a long-term storable biochar and functional biochar product, where on the other hand you can still utilize about 50% of the feedstock for bioenergy or for other purposes. So here is the big potential for carbon dioxide removal, utilizing organic feedstocks and organic residues for it. I already want to conclude a little bit in my two of my last slides, talking about the dimensions for applying pyrolysis. Always think about pyrolysis in a circular economy. So think about the residues and where you have your application. Of course, depending on your application, you can utilize also the carbon carbon sink. And do not forget about the 50% remaining energy, remaining carbon, which is being released through the pyrolysis process. And last but not least, I just want to show you a couple of our Green Carbon Lab infrastructure we have at BEST. We have on the one hand a small scale rotary kiln system providing possibilities to test up to 2 kilograms per hour, but we also have a pilot system which provides up to 90 kilograms per hour of feedstock input. And therefore, thank you very much. I would be very happy to connect with you in the future, and I would be open also to your questions.
Thank you so much, Manuel, for this input. So I noted two questions. One is from our dear colleague Piotr. He wrote two questions, so they are similar, but I give the floor to him to read the question or to say what he's interested in.
Oh, okay, thank you. So thank you. One is general question to you, maybe, Manuel, and I see that many of us are speaking about different substrates, different feedstock for biochar. I just wonder if there should be maybe kind of a hierarchy. If some substrates, very nutritious organic waste can be used for other options, such as composting or black soldier fly, then maybe they should take priority before biochar. And then second question, more precise, is we are speaking here that biochar is infertile, which is true. So how about supercharging the biochar with, for example, the frass coming from, nutrients coming from frass, from black soldier fly, for example?
Yeah. So I try to answer on your first question, but that's definitely not an easy one. I absolutely agree with you that you must not pyrolyze everything, because if you have a feedstock with high water content, for example, for sure pyrolysis is not the best choice. There are other possibilities to utilize and valorize your feedstock. However, I just want to bring in another dimension, not only the process itself, the application afterwards, and the regionality of your field of application is also almost as important and has a direct impact on the choice as the feedstock itself, because it might be that you have directly connected a factory which needs process energy. Then okay, pyrolysis can produce up to 50% of bioenergy. Yeah? Or you have a steel industry quite close to it. Then you can also think of different applications. If it goes, I do not know what the so composting and black soldier fly applications. I think their main predominant product is fertilizer. Am I right? I'm not an expert in it actually, but meaning this only applies if you have directly connections to fields and agriculture. So you're absolutely right. Pyrolysis is only one possibility in such a, I always call it the rainbow of possibilities. Yeah, and you have to select it very wisely. And it is definitely not for every feedstock the optimal one and the optimal solution. And the last, your second question was on, can you help me out, Piotr? What was your second question?
That was about supercharging infertile biochar with frass from BSF.
Yeah. Actually, I cannot answer that question. I'm not an expert in agriculture and charging with nutrients. I'm sorry. Maybe somebody else in this webinar can answer on that.
Yeah. Or we can keep it for the discussion.
Or we can keep it later. Yeah?
Sorry for rushing.
Sorry, Piotr.
We have some more presentations. So next input is by Guillermo Peña Chipatequa, and he is a senior researcher at the Alliance of Biodiversity International and also at CIAT, the Colombian institution part of CGIAR. And he's leading the circular economy platform based on waste valorization technologies and circular bio inputs in Colombia. And Guillermo will give us an input on the RUSTICA project. Please, Guillermo, go ahead.
All right, thank you so much for the invitation. Happy to be here sharing some results and lessons from the RUSTICA project. So at the beginning, I would like to give some context about our research center. We are part of the CGIAR, the network of agricultural research centers around the globe. And here on the pictures, you can see our campus in Palmira is the Americas hub of the Alliance of Biodiversity International and CIAT. And we have also a gene bank securing the global collection of beans, cassava, and tropical forages. We work also globally, and here you can see different countries where we work and have projects at the moment being implemented. And I'm leading the circular economy platform at our Palmira campus. And in the last 5 years, we have been focused on the validation or demonstration of bio-based fertilizers produced from waste through different technologies, and also focusing on how community-based entrepreneurs working on the circular economy can be supported. All right, so let's begin with the RUSTICA project. And this is in this project, this is a project that we worked for 4 years to validate mixtures of products from the waste valorization. And first of all, to give you a context of the region, we focus on different regions, 4 in Europe, 1 in Colombia. And in the case of Colombia was Valle del Cauca. And this region is very, very famous. It's an agricultural hub. So there is more than 1 million hectares of agricultural area, and you can find intensive farming in the flat areas in the valley. So we have a lot of sugarcane growing in that region, but also on the hills is the family-based agriculture that, in the case of Colombia, provides around 70% of the food that we consume. Main crops in the region, as I mentioned, sugarcane. We have also a lot of coffee, bananas, avocado, corn. And all these crops or all these agricultural operations generate about 14.5 million tons of organic waste per year. But at the same time, the region has challenges and opportunities. So on the one side, nationally, we depend on more than 90% of all agricultural inputs are imported. So thinking on the one side on fertilizers, but also animal feed. There is still a low waste recovery or usage rate for organic waste. And but thinking on the policies, something that is evolving is also policies promoting agroecology and the production of bio inputs locally at different scales. So thinking on the family agriculture with maybe you have heard about the different bioferments that on farm can be produced, but also thinking on commercial or more industrial plants, thinking on composting and biochar production and so on. So there is an emerging bio-inputs sector in the region. Okay, now regarding the RUSTICA project, so the objective was to provide sustainable solutions to do this transition from synthetic fertilizers to bio-based fertilizers. And the project focused on different technologies. So in Europe, for example, regarding anaerobic digestion, they were looking on how this, so biogas is not more the focus, but what is inside of the fermenter. And if you can, from this soup, I call this, from this soup, you can extract different nutrient solutions. But in the case of Colombia, we worked on the traditional anaerobic digestion since this sector has still a lot of potential, and there are no more than 10 big biogas plants in the country. We also focused on insect farming using the black soldier fly, biochar production and composting. In the consortium, we were around 16 partners regarding or including public sector institutions, research centers, universities, and also SMEs that in the case of the project were the technology providers, all of them based in Europe. and the project was validated in 5 regions, 4 regions in Europe, so in Spain, Belgium, France, Italy, and for the case of Colombia, Valle del Cauca. Before starting with this slide, the project has different components, but so on the one side, the technical validation of these fertilizers, starting from sourcing the feedstocks in the different regions, looking what is available, and then producing the ingredients at a small scale in the lab, analyzing them also in the lab, and then with that information going further to scale the production in order to develop blends. And these blends were developed also in interaction with different stakeholders that help us also to validate the business models developed in the project. So in the case of every region, we had a stakeholder platform. For Colombia, we had almost more than 80 stakeholders, within them fertilizer companies, waste generators, so including the food industry that is very strong in the region, composting plants, and potential bio-based fertilizer users, academia, government, and also SMEs. And as I said it before, in this region, there is a high biomass availability and strong interest in circular alternatives regarding the high cost of conventional fertilizers. And these are ideal conditions for bio-inputs adoption. And also within these interactions during the different workshops that we had with this group, it evolved that the group now is consolidating as, not, I won't say as an association, but in Colombia we have a kind of entity that is called the agricultural chain organizations, and they have they can have support from the government and also better interaction to have or to get better commercial opportunities, and also to work on quality standards and also the registration process for the different products, since we still have, or we still measure bio-based fertilizers and conventional fertilizers with the same standards. And we know here that that's 2 different things. It's like using complements for nutrition instead of having typical food plate. And that's something that the group is working on that. Here you can see different technologies that we have at the lab, and I'm going to speed up a little bit. And here you can see the business model that we validate with the different stakeholders, taking a food supply center, is the biggest supply center in the region, as a hub. And they are started working with composting for decades, and now they want to include other technologies in order to develop tailored fertilizers for the producers. And we did also the validation, the agricultural validation of the bio inputs. So a blend was developed that included compost, biochar, insect frass, and insect biomass. So I would say the larvae dried and grounded to flour. And we validated that with beans, pumpkin, and corn. Here you can see the results on looking on productivity. And we just evaluate 1 cycle, so we still have to validate more cycles, because on the one side you have the conditions on the soil for decades of conventional agriculture, but what we can see is a kind of tendency and first results that you can get this same productivity with bio-based fertilizers. And now to conclude on the whole project, so we have a high potential on feedstocks for biochar and other bio inputs in this region, and the integrated circular inputs show the strongest agronomic potential. So what was mentioned before on the question, it is better to charge the biochar with another inputs in order to get the better results. And yeah, so long-term evaluation is needed because you have different conditions on the soil, and this kind of platforms and interaction is a good opportunity to work on adoption and scaling. And yeah, the business model co-developed with local actors supports also implementation, and that's something that we are working right now on a proposal for a next project. And yeah, so the region, we will say the region is ready for alternative, this kind of alternative products. So thank you so much, and I'm open for questions.
Thanks so much, Guillermo, for your input, and thanks for staying within 10 minutes. If you have one direct reaction from the audience, then I could take one question. If not, then I would say let's go to our next input. So the next three presenters have an even more challenging task. They only have 5 minutes each, and they will present case studies from their work experience. So first is Lisette Ortiz. She is co-founder of Bioenergy Ingenieros in Peru. Actually founder, not only co-founder, but founder, and she pioneers developing ecological technology for biochar production in Peru. So please, Lisette, if you're here, please share your video, and we are excited to hear from you.
Just whilst we're waiting for Lisette, Martin, that photo is definitely not me.
Okay.
Sorry to whoever it is.
Okay, I think Lisette took over already, but I cannot hear you, but we can see you now. We can't hear you. No. And I think your connection is not good because, yeah, the video is okay. We could also then continue with Tobias right away and come back to Lisette later, if that's fine.
Ready for action.
Okay, so I suggest Tobias to then to do your presentation first, and then to go back to Lisette or your input.
Yeah, fine with me.
But you told me one sentence to introduce you. Tobias is he was a carbon commodity trader for the last 15 years, and he threw it all away for biochar. So that's a strong commitment, right? And he will focus on his experience in South Africa in his input. Gladly, he didn't share a presentation, which is part of ours. So feel free to share your screen if you want, or to do it the way you prefer.
Yeah, I'll free speak. Thanks for everybody for joining. Thanks for the invitation. So I am co-founder and CEO of B10Char. That's the full name of the company. You can figure out what it means. We are located in Switzerland, with our first plant being located in South Africa. Now, Global South, I want to highlight a couple of things that are important to focus on when you're deciding on your location. So there's labor. Is it available? Can it be trained? Feedstock. Is it available in the necessary quantities? Ideally in uniform. The more uniform, the better. Do you have land available for a plant? Is there a legal system which you can somewhat rely on, at least? You know, there is contracts involved with all sorts of parties. if that's not worth it, it makes business very, very tricky in the global south. And is there somewhat of an industrial base there? You can see at the top, that's our plant. At the bottom, somebody is flaring their offcuts. We have to run to get something almost every day. And if you're in the middle of nowhere where you need to buy 100 bolts of something and it takes you 3 days, that is going to be a challenge. We have to drive 20 minutes and we have everything that we need. Spare parts, bolts, metals, welders, and so forth. That is definitely something to look out for. How to decide for what you want to do there. So we already highlighted batch or continuous. This is a continuous plant. It's about 3 tons an hour dry input. And then it's just a factor of how long we can run it before service intervals to give you the yearly capacity, round about 6,000 tons of biochar a year. And one of the most dramatic decisions one will have to make is what kind of plant manufacture. So you can roughly divide it between Western world and China. Western world, you will be paying 20 to 30 times per capacity what a Chinese plant will cost. A Chinese plant will not work out of the gate. Be prepared to do heavy re-engineering, a lot of brain power, engineering power, frustrations. But if you can make it work, then you'll have a cost base that is really, really competitive. So these are the two major choices you have to face. There's obviously quality differences, but Chinese can build good quality, but you're going to be responsible, not them. It's your obligation to make them make good quality. They will not do that when you leave it to them. Spare parts is a huge topic. You better be prepared with the Chinese plant to have a huge inventory. You can see at the right back of our plant, there's a 40-foot container there. That's full of spare parts. So there's some CapEx actually saved up in these spare parts. It's just one of many, many things that you have to consider. In addition to that, operations, this is all about your yield. Before there was a chart where it said 30%, that is almost unachievable. You have to think about there's water content of your biomass. In our case, we use wood chips from waste wood chips from sawmills. 30% water content of the dry mass, there's only 50% CO2. Of that, only 50% you can capture. So if you get 5 to 1, you're already a winner. At 7 to 1, you have a problem. Think about DMRV. Even something in the global south needs reliable data and good controls if you want to go for carbon credits. In our case, we went with a company called Kula out of Berlin. We were very happy with them. Happy to give you references or hit me up if you want to know more. In our case, you always have, if you're going for carbon credits, you have to deploy your biochar in a medium, in most cases agricultural. So there has to be agricultural in the vicinity where you produce. In our case, there's 30,000 hectares of plantations of macadamia nut, avocados, lychees, bananas, citrus. So we don't have that problem, but also don't count on any income. Farmers at the beginning are skeptical. We are winning them over one by one. Giving it away actually helps. We have hired an agronomist to help us do field trials. That is going to win them over with science over time. Last but not least, we believe in B10 to sharing openly what we've learned. We are aware that we will not be able to scale ourselves, no matter what we do, to the size that the the global humanity needs. So we are all for enabling others. If you are sitting on capital, but you want to do a project, but you need a venture partner, we're open for business. And also, if you're interested in our Chinese supplier, a plant supplier, hit us up. We're happy to make an introduction.
Thank you so much, Tobias. So we move right to the next presenter. And the next one is Simon Aigo-Fusi, and he is the co-founder and co-inventor, CEO of Pyrolysis. And you also have 5 minutes, Simon.
Okay, thank you very much, Martin. Can you hear me?
Yes, we can hear you well.
Okay, thank you. Thanks very much for the invitation to present to everybody today. Lovely to see all the attendants and wonderful questions. Pyrolysis really focuses on carbon dioxide removal through biochar, bioenergy, biofuels, and biofertilizers. So a quick overview of our company. We are a pyrolysis technology developer and as well an operating company. I really agree with a lot of what the last speaker was just saying in terms of technologies for pyrolysis. We tend to look at integrating our patented pyrolysis technology with existing value addition processes. So in terms of rural industrialization, there's a lot of waste available, and especially there's typically, if it's a food processor, they need heat. So that allows us to generate that heat and produce the biochar, which we can upgrade to biofertilizers through various routes that we've developed with other partners. So we always look at, as was said earlier by Manuel, creating a circular economy value chain. What's the market opportunity for biochar? Well, if you're looking at it from the view of clean energy, bioenergy generation, figures that we have seen is about 2.8 trillion of annual clean energy investment required in the global south, by the end of this decade. And so there you can see, Africa, South and Southeast Asia, and parts of South America that have the lowest electricity consumption, and then gradually, getting higher. So these areas are prime. And really what makes them even more so prime is when you look at this diagram that indicates that 86% of the world's biomass is located in the global south. So the global south should really be the world's, gigaton scale carbon removal target. And this favors bioenergy and biochar carbon removal solutions. If we look at the market pricing, so CDR.FYI, the price of biochar CDR in 2024 there's quite a range there, but it's quite a tight range compared to other technologies from $113 to $310 per tons of CO2 equivalent. And since 2020, massive amounts of compound annual growth rate in terms of durable carbon dioxide removal purchases, of which the biochar represents 83% of carbon dioxide removal delivery volume between 2020 and 2024. So it's really a market leader when it comes to actually people who are seriously investing in removing carbon and carbon credits that do that. So we've done pot trials of our own using raw biochar, and this is a really important point here. What you can see, we did some, when we first got started, this was like basil, 2, 4, and 8 weeks. So at the top, you've got like coconut coir, and then we blended, 1 part coconut coir to 10 parts biochar. And then we added also some microorganisms, both blended dry and wet. And you can see where it's coconut coir and just biochar, the survival rate is abysmal. So you really need to be very careful about how you use biochar when you're using it for horticultural or agricultural applications. And this chart here, you'll see the worst performance is just biochar and coconut coir. Survival rates are really abysmal. So this was with microorganism, inoculation. And what we learned very early on, that you really need nutrient fortified biochar to get better results. We did another project with another partner, And you can see, this is like in Africa, this was conducted in Nigeria, where we had nutrient fortified biochar with 3 different crop types. So amaranthus is a type of spinach, and then tomatoes. So these kind of like at the bottom here, you can see this is one of our NutriChar formulations. So we trademarked the name NutriChar for a nutrient fortified biochar formulations, and we developed several of them and tested them. So biochar fortified formulations seem to actually beat the NPK, poultry manure, cow dung, and then the soil control with these 2 crop types. And here's some other crop types. So this is tomato, amaranthus again, and pepper. And you can see again, biochar formulations seem to outperform even NPK and, you know, so the other typical locally available fertilizers. So used in forestry, this is a company in Finland that have shown that, you know, you've got nutrient infused biochar and organic infused biochar, and then no biochar. So this is like planting of seedlings. There's a clear improvement when you infuse biochar with either nutrients or organic, you know, formulations. In terms of producing biochar, challenges, some have been mentioned. So another seasonal availability, definitely moisture content, low bulk density, low energy density. You've got to aggregate this stuff. So yes, if ideally you want like 30 to 60,000 hectares within about 25-kilometer radius of where you're going to be converting it, and because high transportation costs, and then of course what's the, you know, production rate of the biochar of your system. If it's not high enough, it's not going to be economically viable. This is a method that we witnessed, you know, it's easily taught, you know, quickly adapted. So open pit biochar production, but you're talking about farmers who want to test this out and see if it's got benefits to them, where they're trained with, you know, some kind of intervention that supports farmers to develop biochar formulations that will work with their crop types. But there's always a risk of fire and smoke inhalation. And then of course you don't have any control over emissions or quality. This is our pilot system that we developed. So it keeps all of those things contained and controlled. And then in terms of, you know, kiln methods of biochar, they require, you know, trained plant operators. It's a continuous process. So you're making over 1,000 tons per year. And then you need a life cycle analysis in order to get the carbon credits. And then, of course, you've got to certify both the process and the biochar, and then you've got to monitor emissions on an ongoing basis.
Sorry, Simon, I think your time is already up, so please, if you can speed up a bit.
Sure. I was just going to say, in terms of fighting climate change, you really can't achieve net zero. This is something, a message that is really coming across now, without carbon dioxide removal. And as you can see, biochar offers a route to carbon dioxide removal, especially when used in agriculture. But there are other applications, especially in construction. So very happy to chat. We're also open to joint venture partnerships to use our technology and know-how, combine it with what you're doing. Thank you very much.
Thank you so much, Simon, for keeping it short. Very interesting. Would be great if we had more time. So maybe we can do another webinar on biochar soon. So let's give it another try for Lisette, please. I think we still cannot hear you.
Can you hear me now?
Yes, I can hear you now. Sorry for rushing. Please, if you can stay within your time, but please go ahead with your presentation. And great to have you here as the founder of the company Bioenergy Ingenieros, which are pioneers in Peru in developing an ecological technology for biochar production. Okay. You're controlling the slides, yes.
Good morning, everyone. Thank you for the invitation to this webinar. In this opportunity, I will talk about the production of biochar in the key ecology of the company Bioenergy Engineers. The localization of the company is in the center of Peru, in Mazamari city. Why Bioenergy Engineers was founded? Because this is the reality, the production of charcoal in Peru. More than 95% the production is artisanal and the subsistence based, carried out the poorest population. This is characterized with the informal employed, high greenhouse gas emission, low performance, low productivity, low yield, and high cost of production. This is the progress in the time of the company. We started with a small metal drum in 2017, then make reforestation. In 2019, we built the first ecological kiln in Peru. It's big, the 5 meter. Then we make a training in Brazil, the Universidad Federal de Viçosa. And in 2021, we built the first ecological kiln system only for the production of charcoal, using wood waste. And now these systems are better because it's possible to produce 2 products, biochar, charcoal, and vinegar wood, and it's possible to use different types of biomass. This is the technology. This is an ecological kiln. Are 4 kilns with 1 gas burner. This is the reason for this is ecological. It's possible that eliminates the gases, principally methane, more than 90%. That operates that this technology without the need of water or electricity. The production is 1 tonne per kilo per week per batch. The cost that this technology is low in comparison with other technologies, and the system of the monitoring is with a pyrometer and thermal imaging camera, and produce high quality of the biochar. This is the yield, the carbonization. 33% is biochar. The temperature, the carbonization is 370. The relation hydrogen and carbon, the ratio is lower than 0.7. It's according to standards international of certification. That 25% that gases condensables is bio oil. This is the characteristic. The smell is smoky. The pH is around 2.5, and this is used in the agriculture. There are some biomass that we use in the carbonization: wood shells, bamboo, coffee husk, rice husks, and banana pins, and different biomass we use. And this biomass now are using in different crops, such as coffee, cocoa, banana, and reforestation. Thank you for your time. This is my contact. Thank you.
Thank you, Elisabeth, so much. Thank you. Even stayed a bit under 5 minutes, so thanks for saving a bit of time. Sorry for everybody that we now have very little time left for discussion. Please feel free to contact the speakers directly. The speakers, if you're okay, please share your email addresses in the chat. I saw that some of you already did, and it was asked a couple of times if the presentations are shared. So we will share the presentations in the Prevent Hub. So for Prevent members, it will be available. if the speakers agree to have their presentations shared. So we will first ask every presenter again if it's okay, and then we will share those presentations. Okay, so we can extend time a bit since it's 3 minutes before the end. From my perspective, sorry if you have another meeting and cannot join, but we will also share the recording of the meeting. Okay, so the first question, general question I have is by Jose Davila. It's a very direct question. Is there any concerns regarding the atmospheric emissions from the biochar process? I'm not sure if he refers to climate emissions. So if any of the speakers has an idea on this, please unmute yourself and share your opinion quickly.
I can take that. As
Okay,
part
Tobias.
of the certification process, you will have to measure your emissions. They're looking specifically for H, CO, and NOx, so nitrogen compounds, because they have climate warming capabilities, especially methane, and you will have to compensate for your emissions before you get credited with certificates for the balance of your reductions.
Great. Thank you, Tobias. Next question. So there were a couple of questions which were answered in the chat. Next question, which was heavily discussed, is by Christopher. So Christopher, if you're still here, you asked about how if we take into account the next 500 years when it comes to carbon credits. So if you want, please explain your question to the audience. I think it's a very relevant point, and it was discussed in the chat, but maybe it's also interesting for our speakers.
Yeah, thanks, Martin. Considering that this question is, of course, highly discussed, maybe we can skip it for the moment and maybe discuss it in another working group meeting, because I'm not sure we can do it within the next 5 minutes. Thanks.
All right. Then the next question I noted is by Siddharth Agarwal. The question is on minimum scale or capacity required for large-scale processing. And it's of course context specific, but if you could give a rough idea about minimum scale and capacity required for large-scale processing. If any of you wants to answer.
I can put my 5 cents to it. So the largest plants you can buy are about 5 tons an hour. That's a maximum. The 3 ton an hour is kind of the sweet spot of large capacity continuous pyrolysis plants, but they also do 1 ton an hour dry input. And the question is, you can probably get away with something like 500 kilos input per hour. Does the scale warrant the investment in getting certified? Is it large enough to make the other fixed costs viable? Like you have to purchase the land or lease the land. You have to have a certain 24/7 operations that is independent of the size of the plant. So you have to really do a good financial model to see whether a smaller plant will actually still be viable. But that's what's available, kind of.
Simon, you want to add on this question? I assume, since your hand is raised. Yeah, but he seems like not moving. Maybe he doesn't hear us. Then thank you. So the next question I have here, biochar is used in completely infertile soil beneath solar installations. So the question is the time frame in which completely infertile soil becomes fertile again and suitable for agriculture. And this was also discussed in the chat. I understand it's not advisable to use it in completely unfertile soils, but if you have any observations on this question, please go ahead. You can take it, Tobias, since we see your face, but also the other speakers. If you have any reaction to this, please let us know.
I can only tackle it from a kind of academic standpoint. I mean, I always compare artificial fertilizers to a drug, and the drug addict is the soil. It gets more and more addicted until it dies. What you have to stop is, adding the substance that makes it dead. That's the first thing to start with. And then you have to add something that brings back life, and that's biochar. So I don't see any other way than actually adding biochar, inoculated biochar, to dead soil. But if you add what made it die, it is going to have a hard time recovering.
Thank you, Tobias, for also answering this question. Guillermo, you want to add on this? If yes, please unmute yourself.
Yes, that what I will add is that it's also important to think about the organic matter, since that's the food of the microorganisms that will provide the nutrients to the plants. So I think it's good also to make sure the biochar with easy accessible organic matter for the microorganisms.
Thank you. Okay, then I suggest we go to the next question, which was to Manuel's input. It was about, like, let's say a factory is only using rice husk as feedstock for operating its boilers instead of coal. Will the ash content be treated as biochar, and is it eligible for any carbon credits? The question was from Trashit Rahul Rai, and it was a direct reaction to Manuel's input. So if you're still here, please unmute yourself. But
okay, so simply wanted to ask.
Yeah, please go ahead.
Yeah, simply wanted to ask if a factory is using rice husk as input for instead of coal, would that be eligible for carbon credits for the factory? And if we can partner with the factory somehow, we can claim them on their behalf.
I'm happy to answer if nobody else wants to.
I think Manuel is not in the meeting anymore.
Okay, the short answer is probably not, because you're getting paid for carbon and not ash. Ash is not organic carbon. It possibly has some inorganic carbon compounds in it, but that's not what you sequestering. So just substituting at least does not give you access to CDR credits. There might be some other forms of avoidance credits that are available to you, but not CDRs, which is sequestration credits.
If we get those tested somehow, are there any benchmarks which we can compare with to understand if there are not any inorganic inputs in it or somewhere like that?
As a base understanding, if you burn something, there's no carbon sequestration.
Great, thank you.
All right, thank you.
Then there's a question by Hasim Pondor, a very direct question. Is there a route biochar to energy base load on the grid? I'm not sure if I understand the question completely. So Hasim, if you are still here, you can explain. Or if you know what is meant, speakers, please go ahead. But I think Hasim is also not in the meeting anymore. Okay, then there's a question by Piotr. I also suggest leaving this for another meeting because it's a more elaborate question. And there are two very direct questions left. Sandra Masonix is asking, can the biochar be customized based on land conditions? Any reactions on this question?
Based on which conditions? Martin, I did not get
land conditions.
Biochar production and characteristics can be modified, can be adjusted depending on the pyrolysis process, can be after the pyrolysis process modified as well through activation or modification. It really depends on what is the need or what are you looking to achieve with that biochar. So just an example, to set an example, iron impregnation will add positive charge on the surface of the biochar, and that will help the biochar absorb or attract more anions, so negatively charged particles or compounds. and so on. So that's just a simple example, but depending on what is the ultimate goal of the biochar application, it can be modified and it can be tailored as well.
Great. Thank you for taking this question, Amzy. And the last question is direct to Lisette. It's by Kathleen Draper, and she asks, most biochar is alkaline, but you said the pH was under 3. So how does that work? I'm not sure if it's alkaline or alkaline. So if you, yes?
I can answer that. Lisette just texted me about that. I just answered in the chat as well that was the pH of the wood vinegar. And actually, Bioenergy Ingenieros biochar's pH is around 7.5.
Okay. Okay, great. Yeah, I see that Kathleen answered. That makes sense. All right. So if there were more questions in the last 7 minutes, I didn't see them. I apologize for that. Also apologize for loading you with presentations and inputs today. So next time we will take more care about having maybe a longer discussions, not so rushed as we did today. But the good thing is that there is a lot of interest on one side. There were a lot of questions from the audience, and also it was very easy to find very good people who were able to share their experiences on biochar from a academic perspective, but also around the globe in case studies. So it would be great to have another meeting on that topic, also align with our GIZ colleagues who work on that topic in a working group. And yeah, hope to see you, those of you who are members of the Prevent Waste Alliance, on Wednesday in our end of the year meeting. And yeah, thank you to everybody. Thanks so much for your inputs, for being here, and see you next time. Have a good time. Thank you, Herwig, for suggesting the meeting.
Thanks, guys. Enjoy.
Thank you. Sorry for the technical issue.